Hi, and this is fifth video of this course, and topic is equation of stellar structures. This is second half of this topic. At last video, we consider the equation of motion for a star. Star is a gas sphere and in the force balance between gravity and pressures. And we derived some equations for stars. At the end of last video, we derived these two equations. One is mass conservation and the other is hydrostatic equation. But we have three variables, mass, density, and pressure. And we only have two equations. So we need another one equation. This equation is so-called equation of state. Here I show equation of state. Equation of state is relation between pressure and density. For an ideal gas, you know this equation, PV equals NKBT. Here, P is pressure, V is volume, N is number of gas particles, Kb is Boltzmann constant, and T is temperature. Let's assume that gas particle mass is Np. In this case, this combination is total mass of gas. And when we divide this mass by volume, we get mass density of gas. Using these two equations, we get relation between pressure and mass density. This is equation of state for ideal gas. But in this case, there is another parameter, T. This is temperature. And here is three possible options after this derivations. And one example is isothermal gas. When gas is isothermal, T is constant. So pressure is just proportional to density. And we get this kind of equation of state. And second option is considering adiabatic gas. In adiabatic process for ideal gas, this combination is constant. Here, gamma is adiabatic index. And for this gas, using this equation, we can derive that V is proportional to rho minus 1. And substitute this relation into here, we get this combination. And this combination is also constant for adiabatic gas. So we get this equation of state. P is proportional to rho to the power of gamma. This is valid for adiabatic gas. And in this movie, we mainly consider this equation of state. And I would like to rewrite this equation of state as here. Gamma is in capital form, and constant is K. In addition to these two cases, there is one more good option. This option is solving T using radiation transfer equations. In this case, we have four variables: mass, flow, pressure, and temperature. And we have four equations: mass conservation, force balance, and equation of state, and radiation transfer. And four variables and four equations. So we can solve that combination. But in this movie, we would like to consider most simplified model and just use this equation of state. Okay, now we have three equations for three variables: mass conservation and hydrostatic equation and equation of state. And there is three variables and three equations, so we can solve this system. And in this case, there is well-known simplification of equations. And this simplified one is called Lane-Emden equation. And in the rest of this movie, I would like to derive the Lane-Emden equations using these basic equations. Okay. Here, there's many equations, but please follow it. Follow me. Using force balance, we can rewrite this force balance as this. We just multiply r squared over rho. And in this equation, here is dpdr. Okay, and we can get relation between dpdr and d rho dr using equation of state. When we take the r derivative of this equation, we get this kind of equations. And substitute this dpdr into here, we get these equations. And here is two variables, mass and rho. And I want to delete one of them just using continuity equations. So in order to use this equation, we take r derivative of this equation. When we take r derivative of this equation, the right hand side becomes this, and left hand side becomes this, and we get dmdr, and let's substitute this relation here. We get this kind of equations, and this final equation only contains rho. So this is a here is only one variable for r, and we can solve this equation under given initial conditions. But before solving this equation, we would like to introduce dimensionless variables as shown here. Here, rho c a n is constant, and rho c is density at the center of star, and a is unknown but in unit of centimeter. So a is length and rho is density. Using this rho c and a, this xi and theta is dimensionless. And let's substitute these, let's substitute these variables into this equation. Let's substitute these variables into this equation. Okay. And using this, d over dr becomes something like this, and d rho dr becomes something like this. Here we just take the radius derivative of this definition and substitute these two variables into the left-hand side of equation. Here, we calculate this combination as this. This is d over dr, and this combination is r squared, and this is rho, and this is also rho, and gamma minus 1 becomes 1 over n. And d rho dr is substituted here. Okay, and putting constant aside, we finally get these final expressions. Okay, please follow calculations. Next, let's consider right-hand side. Substitute these variables. We get this this equation. This is r squared, and this is rho. And substituting this expression, this final expression, and this expression into this equation, we get this kind of equations. And when we set this part as 1, so far A is not defined. So we can set A so that this term becomes 1, shown here. And setting A as this expression, we get Lane-Emden equation. This is very simple equations. It contains only theta and xi. And this is a kind of ordinary differential equations with one parameter and one variables. So we can solve it numerically. This is a numerical solution for Lane-Emden equations. This axis shows theta, and this axis shows xi. And there are many solutions for different n values. In order to solve differential equation, we need initial conditions. But initial condition is defined when we introduce dimensionless parameters. As I mentioned, rho c is the density at the center of star. So at the center of star, theta should be 1. This is one boundary conditions. And in order to, in order not to make singularity at the center, the derivative of theta should be 0 at the center. Using these two initial conditions, we can solve this Lane-Emden equation from here to outerwards. And stellar surface is defined the radius where density equals 0. When n equals 0 case, this blue line, we can solve from center to outward. And as radius increase, the density decreases, and at some radius, the density becomes 0. This is the surface of this star. And for different n, the position of stellar surface changes. And when N is larger solid. When N satisfies this condition, there is no surface solution, no surface for that system. In this case, we need to consider the physics beyond this simplified model, because usually star has a surface, but in this case, there is no surface in this approximation. So we have to go beyond this approximation. Okay. And there is 3 black dashed lines for n equals 0 case and 1 case and 5 case. This is analytic solution for this equation. And if you want, please search or consider by yourself. Okay. Sorry. Sorry. So by solving Lane-Emden equation, we get relation between density and radius. This is a kind of stellar structure. It means just solving these very simplified equations, we can get relation, so we can obtain stellar structures. Okay, here is summary of these two fourth and fifth movements. And I introduced very simplified model for stellar structure. There is 3 equations: mass conservation, hydrostatic equation, and equation of state. And in this case, and for single component star, we get this Lane-Emden equations. This is very simplified one, but we can solve it, for example, just using PCs. And this is very good first step to understand stellar structures. Okay, here is summary of these 2 slides. And here is your homework of this movie. In this movie, I introduce 3 equations, and using that equations and order estimate something like this, you can calculate the temperature of sun using these 2 informations and using these 2 equations. Please do it by yourself. Okay. Thank you very much.